So you see my slides, right?
Yes.
And you hear me. Perfect.
Yeah. Perfect.
Okay, yeah. Welcome, everybody. Glad you came, and thanks for the invitation, Marty. Today I will present about conformal prediction for time series with modern Hopfield networks. This work is actually at this year's NeurIPS conference, and it's joint work with my great colleagues Martin Gauch, Daniel Glott, and Sepp Hochreiter. And maybe just very quick to get an idea who I am. I'm Andreas. I'm a second year PhD student at JQ Linz at the Machine Learning Institute. And my background is mainly in computer science and a tiny little bit in economics. And the talk will be structured like that I first will start about some very basic background information about conformal prediction. Then I will go into our method, HopCPT, and after that we look at the experimental results and maybe some additional insights. Yeah, and then we can have a discussion. But we talked before, if like there is an urgent question in the middle of the talk, you can also feel free to interrupt and ask. Okay, so I would start why we think that uncertainty prediction for time series is an important thing. So we think that uncertainty estimates are actually crucial for action-able predictions, because just having like point estimates and not knowing about whether this point estimate might be right or how far could it be off is really hard to take actions on this, right? And then specifically because like there are a lot of different ways how to quantify uncertainty, we are here interested in a probability P that a certain value that we predict y is in a certain interval of values. In the regression setting, this is the interval, and that is what we have. And we think this is especially relevant in environmental systems, where also mainly our data sets lie in, for example, flood forecasting or solar energy production. But you can see this also very important in other domains, such as supply chains or distributed systems, where you might want to predict your demand forecast, or maybe in finance for something like risk control. And how we approach this is with conformal prediction. And just to get a little bit of an idea what conformal prediction is and what's the cool thing about it. So for conformal prediction, the cool thing is that it provides reliable uncertainty estimates in the form of like sets or interval, as I already said. We have like finite sample coverage. We do not have any assumptions about the underlying error distribution. If whether it's Gaussian or something, it doesn't matter. And you are agnostic to like the underlying point prediction model. You can basically use whatever model you have and what is working for you. And the only assumption you have is like that you have exchangeable data or exchangeability. And if you're not familiar with this concept, you can also think of like IID, which is exchangeability is a little bit weaker than the IID assumptions. So yeah. And the other cool thing is applicable in a wide range of applications. So you can use it for classification, you can use it for regression. There are tons of paper applying it to various domains like drug discovery or image segmentation and whatnot. And now it might be a little bit abstract. So how does conformal prediction actually work? And this example is here not only that you get an idea, so this has nothing to do with time series yet, but just should introduce conformal prediction. And I introduced it with like split conformal prediction, which is an easy way of conformal prediction. There you have like a given calibration data. In our set, we have like a regression example here. So we want to predict like a target that is a scalar. And we have our calibration data set where we have our features and our targets. And then we have like some given point prediction model, which gives us point predictions. And then you need to have a miscoverage level that you specify as you want. For example, if you specify the miscoverage level to 0.1, which means 10%, that means that in your prediction interval in the end, there should be like the probability that your value will be in this interval should be like 90% then. And to do that, you simply use your calibration data, you apply your point predictor, and then you evaluate a so-called non-conformity score. The non-conformity score basically measures how unusual the sample is. And in the regression examples, you can, for example, to make it easy, think about like the absolute error. And here you have this illustrated. So you have here on the plot, you have like the X feature, you have like the Y target, and you have here a very simple linear model as point prediction model. And you see here, like with increasing distance, like this should more or less visualize the non-conformity score, the colors. So darker color means like a higher non-conformity score. And then you can take all these non-conformity scores, you take then the quantile. So here you see now a CDF plot of this. And when we, for example, specify a miscoverage level is 0.1, you take like the 0.9 quantile, check your non-conformity score there, and then use this non-conformity score and simply add and subtract it to your point prediction. And this gives us then this conformal prediction interval. And for a probability of, when we specify 0.1, like 90%, will be the samples of the new data, which are from the distribution, which is exchangeable to the calibration data, will be inside this interval, as we see here. So quite a simple and neat idea. So what's not a problem with time series? The thing is, we said we have this exchangeability assumption, and for the time series, this exchangeability assumption in general does not hold, because we have like these temporal correlations, and we also often have like distribution shifts and trend in such time series data. And the second thing is that conformal prediction gives us a marginal interval. For example, if we use this simple non-conformity score as before, we would get like one interval width for the whole prediction. As you see, for example, in this plot here, so we have now here like the orange is a prediction, the blue line is the real value, and you have here the CP interval, the conformal prediction interval, and at this region here where the error is actually quite small, we could have been like much more narrow. And that is what I mean here with inefficient. Was that a question?
Yeah, actually, this there was a question, and I think it's a good point to ask it. Can you clarify the differences between exchangeability and IID? So just elaborate on that a little more.
I can just say that, like, for exchangeability, what must hold is that if you commute the data points, you have like the same joint distribution. Then you have exchangeability.
Yeah, sure. Just maybe like me add a follow-up question. So can you give an example of a dataset that is exchangeable but not IID?
Actually, I guess no. So not at all.
Okay.
I had this once because I thought of this in another thing, but I have not in my head anymore. I guess there is this example where you put out from ORN, and like in the one case it's exchangeable, but I'm not. I don't recall it perfectly.
Maybe I think it's a. Yeah, I think it's. We can discuss it maybe at the end, but I think what you mentioned is perfectly fine. That if you shuffle the data, distribution doesn't change.
Yeah. Okay.
Yeah.
Another question, or?
No, I think you can continue. Thanks.
Okay. Yeah. Okay. And this example here, as more or less, leads us already to our main motivation, which are time series regimes, or how we see time series. So we think of time series consisting of this so-called regimes, which means that we have like different regimes that are like reoccurring, and there are multiple different. And within such regime, we have like a similar error distribution. We have like similar features in a way, so at least these regimes are identifiable via the features, and we have exchangeability within. And you can think, for example, here this is a very easy illustration. You have like solar radiation, and there might be sunny days and there might be cloudy days. And it might be the case that like on a sunny day, it's very easy to predict how the solar radiation will be because there are no clouds. So you will have low errors, smooth prediction. And in the cloudy, during the cloudy, your error distribution will be different because you have like more errors, right? And then this would be a regime and this would be a regime, just to think about it in that way. And this notion of regimes is what we actually want to leverage with HopCPT. So now to HopCPT, and to give you first a big picture, you can see it as 3 steps. So in the 1 step, we embed like the information which we have for each time step and generate embedding, a representation for each time step. Then we find, given the past time step or the calibration data, the timestamp which are like from the same regime as the current time step that we want to predict. We use here the modern Hopfield network, more to that later. And then we create a weighted conformal prediction interval based on this similarity, what we found in the second step. And now to each step in a little bit more detail. So, was there another question?
Yeah. Sorry. These embeddings, they are vectors of a given length, right?
Yeah. I will get it to
okay.
that.
Yeah. All right. Sorry. Go ahead.
Yeah. So so the first thing is we want to embed these time steps. We want to create representation of these time steps, and for that we have now here a data set. We have like our targets. We have like our features, the covariates more or less, which are given. Then we use more or less all the information we have at our hand. So we use the time series features. We can use the current prediction of the point prediction model. We can use, if we have it, the previous target, and we can use the information about the time step in the form of a temporal encoding. And actually, this embedding is quite simple. We just use like a fully connected neural network where we fed in the information. We add a simple temporal encoding so that we also have this notion of how far is one point from the other way, that we can consider that. And this embedding network gives us then our representation for a certain time step. So the important thing is one time step, one representation. And as you already mentioned, this representation, if you're not familiar with this kind of how you could learn such a representation, is then just a vector of continuous values. Right. And then we want to go to the second step where we find these similar time steps. And this we do by like we associate the similar time steps. And for this, we use the modern Hopfield network. And if you are not familiar with the modern Hopfield network, it's no problem because like the details don't matter that much for this work. It is like an energy-based associative memory network, and the important part is here like an associative memory network. So we have like our observations, our calibration data as like the memory, and then we come like with our current time step, and now we associate the kind of things, so we retrieve the things from the memory again. So just to get a high-level idea. And if you're maybe familiar with Hopfield networks, quite an old concept, then modern just stands for, we do not have like here discrete values, but as I said, like continuous vectors. And to make it even more easy, if you're like coming from machine learning, you might don't know about like modern Hopfield networks, but you probably already heard of transformer attention. And it turns out that if you use like the modern Hopfield network with the energy function like from Ramsau et al.'s paper, and you specify certain parameters in a way, you actually arrive at transformer attention. So the next slide where I go into this, how this association works, you can also more or less think of transformer attention if that is easier. Okay, so now, as I already said, we have like this representation of our current timestamp. So there we have these features and then our encoding network. and we have all the representations of our previous time steps or of the calibration data time steps. And then we simply have here weights, transformation, and then a dot product and the softmax. And this gives us then the weights. And these weights more or less indicate whether this current time step is similar to these other time steps. And this similarity should like represent the similarity in terms of regimes, right? And these are soft weights. So what I mean with that is if like it's like not 0 or 1, it is like from the same regime or not, but rather a soft selection, which also allows you to do something like gradually, for example, decaying the importance of past time steps so that more recent ones are more important or something like that. Okay, now we have the second steps so that we get like the similarity. And with these weights, we create our weighted prediction interval. And yeah, to recap again, if we have this high weight, we think we have points from the same regime, they were also from the same error distribution, and we want to consider these errors. And for low weights, it's exactly the opposite. So low weights, different regime, different error distribution. And this brings us then directly to our formula, how we compute or calculate this weighted prediction interval. We have, as before, we have like our point prediction model mu, but now we don't use like the set of all errors, but we use like a weighted sample of these errors, and the weights are exactly defined by this weight. So if you have a high weight, this observation will be more likely in the sample. And then we take this quantile of these errors and add it to the prediction model. This gives us then this prediction interval. Right, so now we know how the things work or should work. The question is still how we train all this, right? Because we have like the embedding module and the Hopfield parameter, so we need to train it somehow. And it turns out that like classical end-to-end directly learning based on this prediction intervals or something doesn't really work that well, because like we have this quantile calculation, backpropagation through that is kind of tricky, let's say. So we had to think about something else. And our idea here is that we just use like all the errors from the wrong calibration data, and in this case like the absolute errors, and then we want to predict each error based on all the other errors. And the idea here is that if two errors are from the same regime, or if you use like all the errors from the right regime, you should be able to predict the error best. And this is then what happens here. So we basically have the errors, and we want to calculate these errors based on like this attention matrix. And now this is not like this attention weight vector, but rather a matrix, because like now we have like more or less the attention or the association weight from each step to each step. And the diagonal is for sure masked out, because we don't want to use like the actual error to predict the error, right? Exactly, and this is then our loss, and we optimize for this loss. Okay, yeah, just to get an idea whether what I said like turns out to make sense. So we have here like a short visualization of this association for 2 points, and I mean, okay, there are a lot of going on, so you cannot really see, but you get an intuition that for this point, all these lines are like the lines which have the highest association of the past, and the values it chooses, it makes intuitively sense, right? So it's a sample like where we have a high similarity, and the same is for this point, right? So very quick, just some theoretical aspects why what we do even like makes sense, and also to connect it like to existing work. So this, in general, this to have like a weighted conformal prediction is like was not like a novel idea by us, but it was already proposed by Foyle Barber in their paper, where they also proposed HopCPT, which we also compare to. And what they show in this paper actually is that even like if you have non-exchangeability, and yeah, again, I don't want to go into too much detail here, you can like set these weights for the individual points, right? And basically you have to set them low, then this permutation would have a high total variational distance, which would indicate like they are not exchangeable in the sense. And if you set like the weights right, you get like a delta coverage, and this delta coverage refers to I have a specified coverage and I have like the actual coverage, and you just calculate the distance. So you want to be that this is 0 or maybe a little bit positive, but you don't want it to be highly negative. And bottom line is if you set this weights right, then you can like bound this coverage gap also in kind of non-exchangeability. And the second thing I want to link to is like maybe you recognize that we did not yet use like the quantile of the absolute errors, but we had like these two quantiles of just the error values. And this was also already motivated by Xu et al. And their NPI paper, where they already did this, and they showed some asymptotic coverage bounds, and we can also build up on this existing work and show that this is an asymptotic coverage bound hold for us within certain regimes. Right. So hopefully I did not lost here. So if you're not interested in the theoretical aspects, you can join again.
Sorry, if you go the previous slide, that's the lower bound on this delta coverage, right?
Yeah.
Which translates into an upper bound on the empirical coverage.
Yeah, what it means is like you want your delta coverage to be 0 or positive, right? So this delta coverage, oh, there's something missing. So if you have a negative delta coverage, you covered less.
Right, okay.
And basically, if you set the weights right, you want to have here a 0.
Okay. Okay. Can any statements be made on an upper bound for this delta coverage?
You mean like something like that you don't cover too much?
Yes.
I at least I don't know about that.
Okay.
Maybe they have something also that in their paper, but also it's like I mean, if you cover too much, it's unnecessary, and you probably could have been more efficient.
Exactly.
Right?
Exactly.
At least you did not cover too less.
Yeah. Right. Yeah. It's not as bad as undercovering.
Yeah.
All right. Thanks.
That's also actually interesting when you compare models, right? Because it's not really straightforward what is like the best value. Is it best to have 0, and is it more worse if you covered more, or is it actually better? So, but that's an interesting question to ask. Yeah. Okay, I already talked a little bit about related work. And maybe you are already familiar with some CP approaches for time series, and just to put Hop-CPT there a little bit in. So NPI and HopCP. So actually NPI is quite famous, and I guess already implemented in some libraries as far as I know. What they do is they mainly consider like the temporal proximity. So for example, HopCP, which is like this, they introduce weighted CP, they just have like a more or less exponential decay for how important is this point in the past. So you only have like more recent points are important, more far away points are not so important. And this is also something that HopCPT can account for due to this temporal encoding. But HopCPT also like considers this, what I introduced as like the time independent regimes. And then there are like some, I would say, orthogonal approaches. We will get to that later, because basically these adaptive behavior approaches, you can also combine them with these approaches, and we also did an experiment on that. Okay, so yeah, then I guess we can directly go to like this experimental evaluation and then which results we get. So we used like 7 different data sets from 4 different domains. all like environmental data. And we used like 4 different prediction models, like for the base point predictor, random forest, ridge regression, LGBM, LSTM. We mainly oriented us here to existing literature. And we used 3 miscoverage levels, which we evaluated on. And then there are at least 3 metrics which are important. To the delta coverage, I already explained that. So that's basically just like the difference between what you specified and what you get in the end. And you want it to be 0 or maybe slightly positive or maybe slightly negative, but in general, you don't want it to be highly negative, because then actually you covered less samples than you would have wanted. Then the PI width is simply like the average width of the prediction interval, and you also want to have this like small, because then it's like more informative. If you like have infinite wide prediction intervals, you don't really gain anything from that. And then there is the Winkel score, which is not exactly, but you can think of it just of a combination of these 2 things. So it considers both things, whether the interval is wide, and it also considers whether your samples are in the interval. And you also want this value to be low. Okay, so the main result, I would say like the detailed results here. So I know the text is very small, and I don't want to go like in like individual details of this experiment. The main point is that HopCPT actually achieves the specified coverage quite good. So that gives us confidence that these assumptions we made about this regime and the regime identifiability actually hold. This is cool. And the second thing is that HopCPT outperforms the other CP methods, and these are also like time series specific CP methods, really on the majority of experiments. And what I mean with that is like the intervals are smaller and the Winkel score is lower. As you can see here, like for the bold metrics is always like the best metric, more or less. And yeah, you can see that HopCPT does quite well here. And then another thing is we also evaluated against like non-conformal prediction models, like mixture density networks and dropout Monte Carlo. And what we saw there is also when you compare it to these models, which do not have like any guarantee or something, if you assume, or if you say like this approximate coverage is like a hard requirement, then we also outperform these models, because like they very often are like overconfident, especially like Monte Carlo dropout. But that's anyway a little bit hard to compare. Okay, so I would say this is like, is there a question?
Yeah, I think there was a question.
Yeah.
Sankal, go ahead.
Thank you. Hey, Andreas. Would it be fair to say that this is your proposed work is basically a weighted conformal prediction, where the weights take into account the regimes, and those regimes are basically just covered using a neural network?
Can you repeat? Maybe it wasn't. I turn up my volume and maybe.
Sorry, can you hear me more clearly now?
I hear it's a little bit noisy, but.
Okay, yeah, I'm sorry. I don't know why that is. I'll try again. I asked, would it be fair to say that your proposed method is weighted conformal prediction, where the weights are very strongly dependent on the different regimes, and those regimes are discovered using your neural network?
Yeah, I mean, I guess that sums it up. So we have like this idea of these regimes, and we want to find these regimes by learning the according representations.
Okay, so in theory, one could keep this idea of weighting samples or data points by regime, but replace your network with another model for regime discovery.
Yeah, I would say so. Actually, that is, and we also, I will later on also show that like a simple, for example, we also compared like to the simple, but it is actually the next slide, whether, for example, this learning of this representation is even important, or whether we can just use like a very simple KNN approach or something.
Got it. Thank you.
Yeah. So the answer is yes, sure. And actually, that's also an important point for me, that it's not like about like this specific method how you do it, but like one important thing for me is also to think about this notion of regimes, and that this regime and similarity could help you to make conformal prediction better, however you want to approach it.
Perfect. Thank you.
Sure.
Yeah. One other question.
Yeah.
How does the performance of this model depend on the number of time samples that you have for each regime?
Actually, next slide, perfect answer is exactly
Okay.
about those questions.
Okay.
Sorry,
Yes.
Andreas. One more question.
Yeah.
So do you pre-specify the number of regimes, or is that just covered in an unsupervised way?
How that is covered. So this training, how we train it. So we try to actually, you could also think this is actually a point where I'm sure you maybe can improve it. You come up with something like exactly that. That would be ideal to also try like unsupervised in a sense. But what we do here is more or less, yeah, maybe you can call it self-supervised. Actually, I never thought about it, but probably you cannot like that, because like we take these errors that we have and we try to predict like the errors based on the other errors. And the intuition behind this is that if they're from the same regime, we will best predict it, and then therefore the model should learn to take these ones. Does that answer the question?
Yes, it does. Thank you very much.
Cool. Okay. Yeah, then to this slide, and there were already 2 points now about this, because one can think, okay, yeah, using like the similarity metric might work for conformal prediction. Do we even like need this learned representation, which should like more or less represent like this really same similarity? And therefore we also asked that, and therefore we did some ablation experiments where we said, okay, well, it would be like a very simple approach. We just take all the features and then we just use KNN to decide which features are important, or to decide on the similarity. And it turns out that actually like learning the similarity is indeed important. So, and I mean, it's also rather intuitive, right? Because like not all features are like equally important to decide whether a certain data point is from a certain regime. Maybe some features don't tell you anything about that, right? And this also like gives us another interesting insight, and this is what the second question was about, whether how it is about data size, right? And we have for the solar data set, it's interesting because like we have 3 different data sets, and they're all increasing in size. And the bigger the data set, the bigger the difference between like the KNN approach and the HopCPT approach is getting. And we hypothesize this is exactly because like with more data, we can learn a better representation, which better captures this regime similarity. But if you like have really a low data regime, I guess it's a good idea to also maybe try this with KNN, for example. At the very small solar data set, it even is like that the KNN approach is actually better than the HopCPT approach, and interestingly, the best overall approach. So it's also better than all the other CP methods. So the learning here is, yes, this learned similarity really helps you, but if you like have very low data, you can also try something less complex or easier, like KNN, or you can also try something entirely different and come up with your own model to define this similarity somehow, to come up with these weights. Right. Answers this the second question?
Yeah.
Yeah, cool. Okay, so yeah, then another interesting insight. One cool thing. So basically from here we had like these main things, and now I would go over like 3 interesting insights because we have some time left, and maybe they're interesting to you also if you want to use it. The The second thing, what I found quite cool is one neat thing about HopCPT is whenever we predict and we get like the feedback, we can take this new observation and very easily just put it in the Hopfield memory. Without retraining the model or something, we just put it in the memory. And then for the next prediction step, we already have this observation also, which we account for. And we had like one experiment where for some reason, we had this situation that like here we have like the plot of the errors. So on the y-axis, you see here the errors. On the x-axis, you see here chronologically a time step. At timestamp 0, more or less the calibration period ends, and this is calibration data, and on the right, that's test data. And for some reason, the prediction error of this prediction model has a very strong shift downward. So the error is getting negative and even more negative, right? And if you have like normal conformal prediction here, you would have had a problem because like now you would take this data, decide on your conformal prediction interval, which would be then, I don't know, but it would be at least not as negative than here. And then you pretty much would fail to have a good prediction interval here in the test data. And even like in this situation, we see that HopCPT actually achieves a quite good coverage because like we can update this memory and we learn like a little bit of like recency bias, let's say, like the temporal encoding allowed us to say, okay, more recent examples are a little bit more important, so maybe consider this more. And then the interval turned out quite nicely.
So is this plot for one step ahead forecasts?
It's actually, yeah, you could say that it's like a regression. We have like, this is a setting where you have more like covariate features and you want to predict the target.
But the target is just a scalar value, the next value of the time step. It's, okay.
This is the error again. This is,
right.
I guess it's a very simple rich regression model or something, and it for some reason goes off the rails quite a bit.
But this is not a limitation on your model, right? It's just you can also perform multi-step ahead forecasts with this HopCPT.
I mean, in our setting, we only had like this one-step prediction. If you do multi-step prediction, you maybe have a little bit, you have to think a little bit how you would like at the moment it's like we have like one representation for each time step and we take all this previous representation with the errors. So if you now want to have like multi-step forecasts, you would a very easy approach how you would do it is, for example, you look at this time step at the part and tag and do it like in the same way, but for each observation in the memory, you consider the next 10 errors and make a conformal prediction interval on top of that. So that's surely possible, but in this work, we only look at this one prediction.
Okay. All right.
Okay. Yeah, and then maybe also interesting, I talked before about like this orthogonal approaches of conformal prediction for time series, and there's this, for example, this, I guess that one that was the first one, and I guess also the easiest one to explain. It's called adaptive CI, and the idea of their approach is basically you have like an internal coverage level, and whenever you make a mistake, you increase this miscoverage level a little bit so that your interval gets a little bit bigger. And you do this like after each step. And you can also easily think of combine this with all these other approaches. And this is also something we did, because you might think, okay, if I combine adaptive CI with NPy, maybe it is better with HopCPT, with adaptive CI. But it turns out that also like putting adaptive CI on top, HopCPT performs best, and overall it actually achieves like better results than before. So if I would like try it out on a concrete problem, I always like would maybe try to also put adaptive CI on top. Okay, yeah, that we're just like maybe a more detailed insight to get back to the bigger picture and to the conclusion of the talk. Yeah, this is actually the point I wanted to make. Like this concept of regimes and similarity can help you to identify which observations matter, and you can apply this knowledge for conformal prediction. And you could also try like a ton of different stuff, not exactly what HopCPT was doing, but something else. You can start maybe with HopCPT and develop like your own thing on top of that. And the second point for sure is like HopCPT, we saw like achieve state-of-the-art for conformal prediction for time series. And we saw like the similarity-based conformal prediction time series can lead to like more efficient prediction intervals and still like gives you the coverage you want. And yeah, that's actually the end of my talk. So you can check out code papers, everything is online. You can also write me a message if you have a question. And maybe there are more questions now.
Yeah, sure. Well, thanks, Andreas. Great talk, great presentation. One question that I have is that, so what if you get an entirely new regime? Let's say you want to make a forecast of something for the next 24 hours, and that next 24 hours is an entirely new regime, not like any of the regimes you have seen in the past. Then how will this method, especially the weights that you had, these AIs, how will that behave?
That's interesting. So in general, you cannot you can't like say it will work, but if like this representation learning generalizes a little bit, that like let's say like you have one regime is like you have extreme high errors, one regime is you have extreme low errors, and now you get a new regime which are like even higher errors than the first one. And if you have now the situation that like these features which represent the regimes at least have like more similarity with the high regimes, you would at least favor these points and not the others, if this is also like represented in the representation. Then that is something I could think about, but maybe you can also like for sure you can have also an adversarial case where you fail completely.
Okay. Well, since there are no other questions, I will go with my next question, which is, does the network that learns these regimes, this fully connected network, do you have to co-train that with the network that does forecasting? Are they trained together?
Yeah, so the Hopfield and the embedding layer, this is like in once trained with training.
Once trained. Okay, all right, okay. And then does the identification of regimes, does that depend on your point forecaster? For example, if you use LightGBM as underlying method and then use, for example, a linear regression as a second underlying point forecaster, will they give same regimes?
I mean, if they will get, probably you will get similar regimes, but maybe one is you what you mean is like you train HopCPT with the one, exchange your prediction model and use the other one, basically without pre-training HopCPT, whether this would work.
Yeah.
Boy, yeah, I mean, I cannot guarantee. I mean, the first thing is depends what you use like as input features. Normally, we use also the model prediction as input features. If you would not use this, then and for sure you need like to re-evaluate on the your point predictor and the calibration set so that you get actually the errors from there. But since like the thing is maybe even like one point prediction model exhibits like different error distributions in the sense it doesn't capture the difference between like two regimes, but the other one does, and then you could run into trouble. So what we did, we always like trained HopCPT for like a specific prediction model.
Okay, all right. But there is another question from Sankal. Go ahead.
Thank you. Is there any benefit, in your opinion, of training, let's say, two networks, maybe the same type of networks, maybe Hopfield networks, one for regime detection and the other for forecasting?
You mean like how would you do that? You would like have like one point prediction model, and then you have like a second model, which basically what we use from the model in HopCPT is just like the prediction and input, and for sure we have like the errors in the memory, but I don't see at the moment how you would benefit from that in a sense.
Okay, yeah, I was just thinking out loud. All right, thanks.
One final question that I have. There was this slide where you showed the lower bound on this, what was the variable called? Delta coverage.
Yeah.
So have you tested that to see if your empirical results respect that lower bound? Because in the tables that you show, some of these delta cov values were negative. So were those negative values higher than the upper bound? The lower bound?
That is quite, I would say, this bound is more or less to illustrate why this idea would make sense. That if you put like, because I mean, yeah, I mean, you could actually evaluate this, but you would have like, you would need to like calculate the total variational distances on your data set for each point. That would get kind of messy, I guess.
Okay.
This is also like from this paper here, from this weighted conformal prediction paper. I just wanted to give a little bit of, we don't just come up with weighting and doing this, but rather this makes sense. And if in theory, if you set these weights right, then actually you can bound this. That's the main point here.
Okay.
And then we saw, okay, empirically we see our coverage is really quite okay, also compared to the other methods. And also like in this case, for example, where we have this additional shift. I mean, this is something not covered here really. So we thought, okay, that looks good.
Right.
If there are like these bounds, I'm not sure whether this makes no sense to look at this in the paper where you have like really written what are the assumptions that we make here, that we have these regimes, that these regimes come from an error distribution, that we can identify these regimes and so on. But yeah, I guess the most convincing thing is actually the empirical results.
Okay. All right. Well, thanks again. I don't have any other questions. In case I don't know if audience has any questions, we can feel free to ask. Otherwise,
actually, I guess I remember now the exchangeability example.
Right. Yeah. Yes.
It is right. Correct me if I'm wrong, but as far as I remember, it is like that. You have like an urn and you draw from it, and it is not IID because like they get like less, but it is exchangeable because it doesn't matter in which order you draw.
So what was the example that you mentioned? The first part, I'm not sure I got.
You have like this urn where you draw like samples from.
That I don't know, but one example of a series that is exchangeable but not IID is, I think, imagine two Bernoulli distributions. They have different success rates, and then you randomly draw from either one of them. That output will be exchangeable but not IID.
Oh yeah, okay. I have to remember that for the next talk. Because
it's a very, very edge case, so I don't think it has any value, like any practical value. It's a very edge case. So in reality, I'm not sure I can give an example that is exchangeable but not IID in a real time series, not a synthetic one. If anybody knows such a time series, it would be great, yeah, to learn about that. Yep. Okay. Well, Andreas, is there anything else you want to add, or any of the audience?
No, I mean, thanks for listening, for joining. Yeah, check out the paper, check out the code if you want. Write me if you have any questions. If someone is at Neurops, come to my poster. Also, if someone watching this later you can still write me.
Okay, Valerie wants to discuss. Valerie raised hand. Okay, Valerie, go ahead. You raised hand. Oh, okay, it was a clap. All right. Well, thank you so much, Andreas, again, and thank you everybody for your
Thank you
interest.
for inviting.
Wonderful presentation. I personally learned a lot. Thank
Cool.
you.
Thank you.
And yeah, have a nice day or a good night, everybody. All
Sure.
right. Yeah.
Bye.
Take care. Bye-bye.